Thanks to CuriosityStream for supporting PBS Digital Studios. How can we use a simple modern puzzle to solve Schubert's complicated classic geometry problems? Here's two lines in three-dimensional space. Can you describe all the lines that intersect both of these? Or, to complicate things, here's four lines in three-dimensional space. How many lines can you draw that intersect or touch all four lines? These are exactly the kind of intersection problems that fascinated Hermann Schubert, a mathematician in the late 1800s and the namesake of everything we're about to discuss. He actually computed all sorts of wild enumerative geometry problems, like the number of twisted cubics tangent to 12 quadrics, which is apparently 5,819,539,783,680. And maybe that exact number doesn't seem particularly important, but the fact that Schubert was able to figure it out is pretty amazing. He did this calculation with very few modern mathematical resources, which is why one book compares it to landing a jumbo jet blindfolded. Schubert simplified these kind of problems by moving lines around until they were in a specialized position, like this or this. As long as we're very careful about how we do it, specializing lines doesn't change certain properties, like how many lines intersect them, but it does make it easier to compute. Schubert's justification for doing this was slightly sketchy. Making his calculations rigorous is actually the 15th problem on David Hilbert's famous list of influential math problems in the 20th century. But here's the part I think is wild. Even in these specific cases, how does one possibly compute the number and type of intersecting lines? In some cases, you can make a high school-style geometry argument, but what about in more complicated or higher dimensional scenarios? This is where the puzzles help. There are three pieces: an equilateral triangle with red sides, an equilateral triangle with blue sides, and a parallelogram, exactly twice the size of the triangles, with two red and two blue sides. We'll always label the red sides with 0 and the blue sides with 1. The goal of the puzzle is to arrange any number of pieces into an equilateral triangle. Only edges of the same color can touch. The pieces can be rotated. The triangles have 2 orientations and the parallelogram has 3, but not reflected. So this is not a piece. Here's some examples of filled-in puzzles. What patterns do you observe? As always, you're welcome to pause and conjecture, or make your own puzzles. Let's count the blue edges along the side of a puzzle. For example, on the left side of this big puzzle, there are 4 blue edges. The right side also has 4 blue edges, and so does the bottom side. Each side of this puzzle has 2 blue edges. The littlest puzzle clearly has 1 blue edge on each side, and same for this one. That seems to be a pattern. All 3 sides of a puzzle have the same number of blue edges. We'll label that conjecture number 1. Also, all 3 sides have the same number of red edges. But since the sides have a fixed number of total edges, those are equivalent conjectures. Now let's count the number of blue triangles and red triangles within each puzzle. Do you notice a relationship between the number of blue edges along a side and the number of blue triangles? Or red edges and red triangles? Again, there seems to be a pattern. The number of blue triangles is the square of the number of blue edges along a side, and the number of red triangles is the square of the number of red edges along a side. We'll call that conjecture number 2. If you want to try and prove the conjectures yourself, pause here. To help with the proof that I'm going to give, let's introduce some variables. N is the total number of edges on each side, and K is the number of blue edges on each side. And N minus K is the number of red edges. Now, start with a filled-in puzzle. We're going to contract it in a very particular way. Shrink each red triangle, maintaining its ratio so it stays an equilateral triangle, but shrinking the edge lengths. Simultaneously, shrink the lengths of the red edges on the parallelograms. Don't change the lengths of the blue edges. Eventually, after the edge lengths of the red triangles go to 0, we are only left with blue triangles. Notice that during and after this shrinking process, the entire puzzle maintains its shape as an equilateral triangle. How does this prove conjecture number 1? After the shrinking process, the puzzle clearly has the same number of blue edges on each side. Moreover, the number of blue edges on each side was preserved during the contraction process. So each side of the original puzzle must also have had the same number of blue edges, which we're designating with the variable k. Since every side has n edges and k blue edges, they must each have n minus k red edges. What about conjecture number 2? To prove that, we're going to use triangle area. Normally we think of a square, like this, as having area 1. But now, let's think of a single triangle in our puzzle as having area 1. The puzzle has n edges along each side, and so it'll have n squared triangle units. That is, if you filled it with only triangles and no parallelograms, it would contain exactly n squared triangles. After contracting the puzzle, it's made entirely of blue triangles, and there are k edges on each side. So, it is k squared triangle units. It contains k squared blue triangles. The number of blue triangles didn't change during the contraction process, so the original puzzle also contained k squared blue triangles. Doing the contraction process in reverse, shrinking the blue edges, shows that there must be n minus k squared red triangles. Challenge problem. Using this information, how many parallelograms are in each puzzle? So let's say I give you a blank puzzle with one side colored, like this. You know a lot about the filled-in puzzle. It has 2 blue and 3 red edges on each side. It contains 4 blue triangles, 9 red triangles, and 6 parallelograms. That's a lot of information from just one boundary. But how does this help us with Schubert's problems? We want a way to rigorously compute intersections of lines. Intuitively, there's 2 basic types of lines that intersect both L1 and L2. First, any line that goes through their point of intersection, like this or this, works. Now, notice that any 2 lines intersecting at a point are contained within exactly one 2-dimensional plane, like this. You can prove this with geometry or linear algebra, or just observe it in the real world. Take 2 crossing sticks. There's one way to lay a piece of paper flat over them. The second type of line that intersects both L1 and L2 are the lines contained within this plane, like this or this. But to solve this more rigorously, we'll describe different sets of lines using a template, the collection of all lines that touch a fixed blank and are contained within a blank, and fill each blank in with the smallest one of the following: 0D point, 1D line, 2D plane, or 3D space. We'll encode the template in a string of 2 zeros and 2 ones, where the ones indicate how you fill in the blanks. That's a lot to follow, but let's see some examples. This is the collection of all lines that touch a fixed line and are contained within 3D space. So it's 0, 1, 0, 1. If all the lines were contained in a plane, like this, we'd move the second one forward, so it's 0, 1, 1, 0. This is the collection of all lines that touch a fixed point and are contained within a plane, so it's 1, 0, 1, 0. What does 1, 1, 0, 0 indicate? It's all the lines that touch a fixed point and are contained within a line. But there's only one line contained within a line, so the collection has size 1. We want to compute lines that are in multiple collections. For example, what's the overlap between all the lines through this point and all the lines through this point? Well, remember from geometry class that there's only one line between 2 points. So we can write that as 1, 0, 0, 1 times 1, 0, 0, 1 is equal to 1, 1, 0, 0. The collection of lines through this point and this point are just one line. But these problems can get much trickier. This is where the puzzles come in handy. We'll use the same example from before. We read each side of the puzzle from left to right. Write the code for the first condition, intersecting L1, on the left side, and the code for the second condition, intersecting L2, on the right side. Then start to fill out the puzzle. There's 2 ways to do it, like this or this. The bottom of the puzzle is either 1, 0, 0, 1, all the lines through a particular point, or 0, 1, 1, 0, the lines contained in a plane. This corresponds precisely to our geometric picture. This puzzle, invented by mathematicians Alan Knutson and Terence Tao, is computing the result of imposing multiple conditions. We can write this algebraically. 0, 1, 0, 1 times 0, 1, 0, 1 is equal to 1, 0, 0, 1 plus 0, 1, 1, 0, where essentially multiplication means and addition means or. That is, the lines which intersect a fixed line and intersect another fixed line are either the lines that intersect a point or the lines contained in a plane. How many lines intersect all 4 of these lines? That means we want to compute 0, 1, 0, 1 times 0, 1, 0, 1 times 0, 1, 0, 1 times 0, 1, 0, 1, which computes the overlap between all the lines that intersect each of these 4 lines. Using the last computation, we can simplify it to this. Just like normal addition and multiplication, we can distribute, and anytime we need to solve a multiplication problem, we just use the puzzle, like this. Then we repeat that process until finally we get to 2 times 1, 1, 0, 0, 2 lines. We can actually see this geometrically. One line goes between the 2 crossing points, and the other line is the intersection of the 2 planes containing the pairs of lines. Which brings me to a quick caveat, a technical detail. Most of today's episode is actually about complex projective space, but to simplify matters, we fudged it by working in real space. That means I was actually using line in 3 dimensions as a stand-in for 2-dimensional subspace in 4-dimensional complex space. Speaking of higher dimensions, a puzzle with n edges on each side, k of which are 1s, gives us information about the k-dimensional subspaces within n-dimensional space. That's part of what's amazing. These puzzles work even when we can't literally envision the geometry, in higher dimensions and far more abstract situations. See you next time on Infinite Series. This episode is brought to you by CuriosityStream, a subscription streaming service that offers documentaries and nonfiction titles from some of the world's best filmmakers, including exclusive originals. I'm very excited to sit down and watch The Origami Code, a documentary about the beauty and surprising scientific uses of origami. Get unlimited access today, and for our audience, the first 2 months are free if you sign up at curiositystream.com/infinite and use the promo code INFINITE during the sign-up process. You all had a ton to say about the worrisome lack of a foundation for mathematics. Alan asked, can pure logicists prove almost everything using all but the 2 axioms they don't like? And then maybe they should be unsure of the validity of whatever is remaining if that's the logicist position. That's a good question. Unfortunately, some of the non-logical axioms are really necessary to build all of modern mathematics. For example, the axiom of infinity gives the existence of the natural numbers. Certainly one could study the remaining axioms, but the logicists really wanted to find a logical foundation for all of modern mathematics. Goldfish asked a wonderfully detailed and curious question about Dedekind cuts. It's all fun to read, but here's my favorite part. Things get even more confusing in my head when I bring to the table the fact that rational numbers are countable. If rational numbers are countable and every irrational number can be defined as a gap between 2 rational numbers, then it seems to me that there must be a way to map every irrational number to a natural number via its corresponding rational number, right? I find this countable-uncountable thing sort of amazing too. I'm with you, Goldfish. The real number line is weird. But there are a few responses to your question. Here's one. A Dedekind cut is a gap in the rational numbers, but not a gap between 2 rational numbers, which is a weird distinction. A Dedekind cut is simply a division of the rationals into 2 sets, where all the elements in one set are bigger than all the elements in another set. Using the square root of 2 as an example, there's no rational number immediately above or below the square root of 2. For any rational number you select that's bigger than the square root of 2, there will always be some rational number smaller than that but bigger than the square root of 2. But there's another answer to your question that might be related to Ringworld's question. How do you get all transcendental numbers from Dedekind cuts? it would seem it would only allow you to construct algebraic numbers. Algebraic numbers are the roots of polynomials with rational coefficients, and transcendental numbers are everything else. Dedekind cuts are all possible ways to split the rational numbers into two sets, and many, actually most of them, aren't describable in the way the square root of 2 was. Those are the transcendental ones. Finally, Stephen recommended this wonderful graphic novel about the history of logic and the search for math's foundation called Logicomics. I can't believe I forgot to mention it. The book is so good, and I'm glad you did. Thanks, Stephen.